Oh, good afternoon, evening, ladies and gentlemen. This is Roger W. Knight, and I decided to record another lesson uh, for those of you who are homeschooling or just want to review. Only this time we're going to do physics. Basically, Newton's equation of gravitation and mass. Now, what we have here is the basic Newtonian equation is like so. You have force equal to gravitational constant times the mass of one object times the mass of a second object divided by the square of the distance between the centers of the two objects. This is a fundamental equation. It's necessary for calculation of orbits. It's necessary for placing spacecraft into orbit around the moon or around Mars or elsewhere in the solar system. It's what astronomers use to literally calculate the masses of distant stars or estimate them, and especially if they find binary stars where they orbit each other. And then they can get an idea on what the attraction rate is between them and at least their relative masses, and then with the gravitational constant, a good estimate of their actual masses. Oh no, I hope the COVID's not affecting me. So we have this here. The most important factor, fundamental factor, is the gravitational constant. Now it's a very important constant. Here I have it, it's equal to 1.069 times 10 to the minus 10 in US or English units, the FPS system, where we have pounds as the unit of force and pound mass as our unit of mass. If you multiply this number by 32.174, then you'll get the gravitational constant, where the unit of force is pound force and the unit of mass is the slug, or slug squared. And then you see it's equal to 6.674 times 10 to the minus 11 in the meter kilogram second system, MKS system, where the unit of force is the Newton and the unit of mass is the kilogram. And a meter squared there, just like we have foot squared up here. We have a slightly different number, 6.674 times 10 to the minus 8 in the CGS system, where the unit of force is the dyne and the unit of mass is the gram, and of course we have centimeters squared there. So it just kind of changes the value of this power of 10. You know how the metric system is. You switch from CGS to MKS, then you have to sort out what power of 10 your value is. But, we have the multiplication and division by 32.174 to go from pounds and pound mass over to pound force and slugs. But anyway, one of the things that you will have noticed is that when you start studying science and engineering and physics, is that a lot of our technology seems to, at least in education, has been taken over by what I call the cult of the meter. You know those guys. Those guys sit there and wonder, gee, why don't you Americans change your road signs over to kilometers and stop selling by gallons your milk and your gasoline and other such things, and just join the rest of the world? Well, the rest of the world didn't walk on the moon. We did. But the thing is, is that it comes out that the cult of the inch might be the best way to describe our aerospace industry, which is an outgrowth of the aircraft industry. When I worked at Boeing, the inch was the fundamental unit of measurement of the Boeing company, because everything in the aircraft was designed in terms of inches. Body stations were set before and after the division between the cockpit section, or the flight deck section, which was called section 41 on most of the birds, and the rest of the plane, and it was called station 360. Just an arbitrary designation, because 10 yards in front of this was the 0 point of the coordinate system upon which Boeing designed and built its aircraft. And 360 inches is 10 yards or 30 feet, or for that matter, 5 fathoms. And 360 is a popular number in a lot of our mathematics and pre-metric unit systems of weights and measures. You'll see it in the number of degrees in the circle. You'll see multiples of 360 crop up in our time units. Not so much the 24-hour day, but that the number of minutes in a day is 1,440, which is a multiple of 360. The half day, represented by the 12-hour clock, is 720 minutes. That's equal to that's the number of degrees in 2 laps around the 360-degree circle. And of course, 360 seconds is the number of seconds in 6 hours, a quarter day. So you see 360 shows up here and there. In the pre-metric Japanese system of measures, 360 shakus is a cho, and then 36 chos is a ri. So they seem to like the number 36 in the pre-metric engineering of Japan. But there's another interesting thing that the cult of the meter and the cult of the inch conflicted in our aerospace, and this is the famous case of the Mars Climate Orbiter. I'll show you on this. This is part from the Wikipedia article. You'll see that the planned trajectory was to hit 260 kilometers from Mars, and the actual trajectory was estimated to have gotten within 57 kilometers of Mars. Now, Mars has a pretty thin atmosphere. It's only 0.15 psi at the surface, about 1/100th of an Earth atmosphere at sea level. But still, 57 kilometers up, you still have a few molecules per cubic foot of space, and apparently that's a few molecules too many for the orbiter, and it either tumbled and crashed onto the surface of Mars, or it bounced off out into deep space somewhere. No one knows where it is. We can't get any radio signal from it. Maybe the radio sending device was damaged somehow, or it's pointed in some direction other than Earth, and its gyroscopes aren't working to orient it toward Earth. So we lost the spacecraft. And if you read the Wikipedia article on this, it explains that the reason for this was that software supplied by Lockheed Martin produced results in pound force units. The trajectory calculation software that used these results, which was supplied by NASA, was expecting it to be in newtons. And there are 4.45 newtons in a pound force. And so, without putting that factor in, there was a miscalculation on the impulse submitted by their thruster fires, little rockets attached to the thing to adjust its orbit, to adjust its trajectory relative to the rest of space, say planet Mars. And so, because of this error, it got too close to the planet and was damaged by running into too much atmosphere above the surface of the planet. And everybody says, well, this is why we should have gone fully into the metric system, or why we shouldn't have bothered with the metric system at all. But this is just one of those dumb little mistakes that could have been fixed by one line of code. What line of code does that say? A line directing that the result in pound forces be multiplied by 4.45 to get newtons to be fed into the rest of the software. That would have fixed the problem, and then we would have been enjoying the Mars Climate Orbiter the entire time it operated in orbit around Mars. But we lost that, and we lost the money we spent on that. And there's another little thing here. The propulsion engineers, there were two navigators at least that spotted the discrepancy, and they tried to warn about it, but because they did not follow the rules about filling out the right form, they were ignored. Can you believe that? That just sounds like a corporate bureaucracy. That sounds like Boeing. That sounds like NASA. But it really isn't the problem that we Americans prefer our units of weights and measures as opposed to the rest of the world using their weights and measures that really caused the problem. The problem was somebody effed up. It's really that simple. Now you might say, why is the aerospace industry so inch-oriented? Well, it's kind of an accident of history. You see, the nations that used inches in their manufacturing, the United States, Canada, and Britain, defeated the nations that were tending to use millimeters in their manufacturing, Germany, Italy, and Japan, particularly in the air war. And so, with Germany ruined and Japan ruined and destroyed, much of the rest of Europe badly damaged from the war, much of the western part of the Soviet Union damaged from the war, much of China damaged from the war, you name it, it was damaged. It pretty much left Americans and British and Canadians with a virtual monopoly on everything aircraft. So, you go to any airport in the world, it lists its elevation in feet, and the altitudes are in feet, and the air traffic control is communicated in English and in feet. There's lots of former British Commonwealth nations that, while they have kilometers on their road signs, they know what feet and inches are. And I found that even when I was in Kenya, a former British Commonwealth nation, where the local folks are definitely not English, they speak English along with some Swahili. They seem to be bilingual in that. And when it comes to up close and personal distances, and distances for their houses and their local construction, they're kind of feet and inch oriented, even though their road signs are in kilometers, and their speedometers on their cars measure in kilometers. At least they don't have, I haven't seen any cars in Kenya that were old enough to have miles per hour speedometers, like classic cars in the United States. So that's kind of that, with the cult of the meter and the cult of the inch, so to speak. But, it's upside down. We still have the Gfactor. Here's the problem that NASA runs into and why it had to have adjustment rockets, thrusters, on all of its probes it sends around the solar system and around the moon. The reason it is because we only know G to about 6.67, and maybe 4, maybe 3, maybe 5 is this last digit. And in the English units, we get 1, a 0, a 6, and then that 9, maybe it's actually a 7 here, maybe it's a 9.2. It's kind of, and you multiply by 32.174 to get it into pound force and slugs. Squared down there, the best measurements we have are to these 4 digits. That's it. We really don't have much better. Now, a number of experiments have been done, updated versions of the Cavendish experiment that first measured the Gfactor, the gravitational constant, or implied it. He was trying to come up with the density of the Earth, and he was close to the actual value of the mass of the Earth. But still, because of the uncertainty in the value of the one of the most fundamental constants of the universe, the gravitational constant, NASA and the Soviet and the old Soviet or the Russian Space Agency nowadays, the European Space Agency, the Chinese Space Agency, every time they send a rocket up above the atmosphere, they have, whatever probe they send has to have little thrusters on there, which they should do anyway for steering, because even though it's a real long shot to send a probe all the way out to Mars on a Hohmann ellipse orbit and get there, they still have to make the final adjustments to insert into orbit around Mars, or to land on Mars, or anything else they got to do with Mars, not to mention going out as far as Jupiter or Saturn, or flying by Pluto and Ultima Thule and other such distant objects. It is really the real issue, due to the fact that G is only known to that digit. And the experiments, they come up with measurements that have lots more digits than this, but they don't agree with each other past this 4. Which is really crazy. I can tell you why. Because no matter how carefully you design the experiment to measure the attraction between two big heavy masses, say they're 10 pounds or 100 pounds or 1,000 kilograms or whatever size of masses you're using for your experiment to measure the tiny amount of force of attraction between them, using, say, a torsion bar or some such that multiply the effect, you're still operating right next to a great big mass called Earth. You know, the center of which is attracting us at a rate of 32.174 feet per second, or about that. So that's the limitation, but still, this is what we have. Yet, with this, we can actually calculate an estimate for the mass of the Earth. You see, you take this Newton equation, you do a little algebra to switch the units around, and if you look at this, if you know 4 of these values, one of the masses, the G constant, the distance between the center of your test mass that you know and the center of the mass you want to find out, and you know its force, you can calculate the mass of the other object. And the other object could be Earth. Now, let me show you what we did. And this is really simple. You can do this yourself. The algebraic manipulation. This involves a little bit of algebra. You middle school students, yeah, this is what this stuff is good for. You know, you've been wondering, well, gee, how can I solve for X if I don't know what the heck A, B, and C are? Well, you know, you find out what A, B, and C are. That's how. If you know A and B, you could probably solve for C. If you know A, B, and C, you could solve for X. You take this equation, and you want to measure one of the masses. I use the letter E to indicate mass of the Earth, because that's what we want to find out. We can use a known mass, say a kilogram or a pound or a slug or whatever. By dividing it from here, from both sides, you get it in the equation. You divide G from both sides, you get it in the base of the equation. You multiply the force from both sides, you get it up here, and the R squared value. So you have this equation. If you know these 4 values, you can calculate a good estimate of the mass of the Earth, which is a huge mass, of course, because it's everything in the world, literally. So we put some numbers. Here is where we use it in English units. Mass of the Earth in pounds mass. The force is 32.174 poundals because the mass that we're using is 1 pound. We have 1 pound mass here in the base. That means the force is going to be 32.174 poundals, because a weight of 1 pound, say this scissors weighs 1 pound. If I let go, it accelerates 32.174 feet per second toward that. And then as it sits on the table, it exerts a force of 32.174 poundals, or 1 pound of force. That's what 1 pound of force is, 32.174 poundals. It's a kilogram of force is 9.8066 newtons, because that's the weight of 1 kilogram while sitting on a table. So we have 32.174 here. The radius of the Earth, the distance between here and the center of the Earth, is about 3,960 miles. This is based on a common estimate of the average radius of the Earth, of the average diameter of the Earth, of 7,920 miles, which happens to be the number of inches in a furlong, which is a weird little coincidence, and makes you wonder if the English knew about the size of the Earth. It's when they defined what are now the modern values of inch, foot, yard, fathom, furlong, and mile. At least they got as far as inch, foot, yard, and furlong back in the Middle Ages. The fathom and the mile kind of came later, maybe. Although the idea of an 8 furlong mile long predated the Parliament under Elizabeth I that formally defined the statute mile as 8 furlongs. So you have 3,960 miles, that's the radius of the Earth, the distance between here and the center of the Earth. We just multiply that by 5,280 to get feet. Square that gets your square feet. And then you divide by the gravitational constant in the FPS system, 1.069 times 10 to the minus 10. The known mass is 1 pound, so 1's an easy number to multiply by. And we get our estimate of the mass of the Earth as 1.3 times 10 to the 25 pounds. 10 to the 25th power of pounds. A lot of pounds, but that's how big the Earth is in pounds mass. Divide that by 32.174 and you get the size of the Earth in slugs. You divide that by 2,000, you get the size of you get the mass of the Earth in tons, short tons, and such. You can multiply this value by whatever the ratio is between the pound and whatever unit you want to go. No. Let me see. Oh yeah, divide by 32.174, you get the mass in slugs. Divide by 2,000, you get the mass in short tons. Multiply by 16, you get the mass in ounces, and so on and so forth. So we can actually calculate, if we know these other numbers, a good estimate of the mass of the Earth. Isn't that kind of neat? Say you want to think metric instead. Well, I show you the same equation with the metric values. In the MKS system, 9.8066 is the number of newtons that a kilogram of mass weighs, and we have in the bottom of the equation the 1 kilogram mass, and 1's an easy number to multiply and divide by. The distance from here to the center of the Earth in kilometers is 6,373. I just decided to zero out the rest of it because, you know, the Earth is an oblate spheroid, so we'll just take 6373, which is the metric version of 7920. If the Earth was a perfect sphere, the diameter would be about 7,917 point something miles, but 7920 is kind of a traditional value in that that's a multiple of 360, and it kind of fits in with the diameter of the moon being 2160 miles and the diameter of the sun being 864,000 miles. Another really interesting coincidence is that the radii and diameter of the Earth, Moon, and Sun tends to be multiples of 360. Those medieval English, you would think you get the idea that maybe they had an idea of the size of the Earth, the Moon, and the Sun. Maybe. Just like the guys who invented the meter had an idea of the size of the Earth, so they could guesstimate. They estimated 1/10,000,000th of the distance between the North Pole and the equator. That's how we get the meter as long as it is. They had a good idea of the size of the Earth. And if you look at certain, and it wasn't that hard for them, they used measuring equipment that Archimedes could have used, or Imhotep, or maybe the Chinese of 4,000 years ago could have, or the Mayans. Any of these cultures could have easily, by going north and south, measuring how high the Polaris star or the North Celestial Pole rose or fell with their distance, and carefully measured the distance, could have accurately determined the size of the Earth. Which is why we have a lot of ancient monuments that seem to indicate the size of the Earth, if not the mass. So we have 9.8066, which is the acceleration of gravity at in meters per second per second. It's the number of newtons that a kilogram weighs, and that's the force drawing the 1 kilogram mass toward the center of the Earth. We have the radius of the Earth in meters. You add 3 zeros to make it meters. Square that. Divide by the gravitational constant of 6.674 times 10 to the minus 11, and we come up with 5.968, or just shy of 6 times 10 to the 24 kilograms. And that would be like you have 6 times 10 to the 21 metric tons. That's the size, that's the mass of the Earth. So this is a simple lesson in how Newton's equation can be used to calculate some extraordinary things, such as the mass of the Earth. And then, knowing that, we observe the orbit of the moon. We can calculate the mass of the moon based on how the Earth and moon rotate around each other. And the moon seems to be 1/81st of the mass of the Earth, because the common point of rotation between the Earth and the Moon, as they orbit each other, appears to be that much distance from the center of the Earth toward the center of the Moon. And then we can observe our orbit with respect to the Sun and get an estimate of the mass of the Sun. And then with other such observations, astronomical observations, we get estimates of the mass of the planet Mercury, planet Venus, planet Mars, Jupiter, its moons, Saturn, its moons, Uranus, Neptune, Pluto, all the way out to Ultima Thule. All this by simply observing their orbits, calculating everything carefully, and using this gravitational constant, which is why we had good estimates of the masses of these solar system bodies even way back in the 1800s. So there's my quick lesson on simple application of our mathematical principles in terms of calculating the mass of the Earth using Newton's equation. Have a nice day, and feel free to look at my other videos.